lihat spot juga kemarin agak ngedrop ya Bu, spotnya.
Ya, iya, pernah.
Kan mahasiswa langsung itu, ini gini gimana Ibu? Udah, udah mau mulai ya? Nuhun ya Bu,
Ya,
sudah diundang. Terima kasih.
sami-sami.
Halo, selamat pagi. Salam sejahtera.
Selamat pagi, Dr. Mages.
Okay. So, how are you all? You all fine?
Alhamdulillah, we're fine here in very nice weather in Bandung at the moment.
Okay. So, how is the COVID situation? Is it reducing or how?
The new cases has been dropped, 10 every day in Bandung. Because I haven't checked yesterday's report, but yeah, last week report is only like 5 per day.
Oh, that's very good, really.
Yeah, in Bandung, not in Indonesia.
Yeah. Okay.
So yeah, and some of the school have been open for, so most of the school now implementing the hybrid learning. Some of the students at school and some of the students join an online class, something like that.
Okay.
Yeah, but yeah, we still need to what we call to implement the protocol, they have
SOP.
very tightly the SOP. Okay, Dr. Mages, I need to confirm to you about the today's topic is about data analysis, but I, as far as I remember, that we have educational research instrumentation. Is it only involved in this part, or does it have to be in the next?
It's about the instrumentation. I will talk next week.
Yeah. Okay.
The reason is I don't think I can cover everything in one slot, 2.5 hours. Yeah, it will be a lot. Even for the data analysis, I will show you like this is what I'm going to talk, for today. But I don't think I can reach one-way or two-way MANOVA or repeated measure MANOVA. I don't think I can reach here. That's why I put it in red. So I try to cover the whole from descriptive until repeated measure ANOVA. So one way and two-way MANOVA and repeated measure MANOVA, and there's also something called MANCOVA. Yeah. So I don't think I can cover this. That's why I put it in red. So maybe we can shift this for next week. I will combine with instrumentation and factor analysis.
Yeah. Okay. Thank you for the confirmation, Dr. Mages.
Yeah.
All right. Should we start now, Bu Herani?
Yeah.
Karena it will be like a very long discussion with you for Dr. Mages.
Yeah.
Oke, kita mulai saja. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah, Dr. Mages, here we already have our beloved students. We also have some of our colleagues here from the Education Department. For today's, let me introduce them one by one. Okay.
Yeah.
Dr. Hernani, you already met.
Yeah.
We also have Ibu Wiwi Siswaningsih here.
Iya, selamat pagi. Good morning.
Yeah, good morning, Ibu Wiwi.
Ibu Wiwi, and also Ibu Soja. We have Ibu Soja here.
Selamat pagi, Dr. Mages.
Ya, selamat pagi, Ibu.
And also we have Ibu Fitri Hoirunisa.
Okay, selamat pagi, Ibu.
Bu Fitri still mute, Bu Fitri.
Very good morning, Dr.
Yeah,
Mages.
good morning. Good morning.
Yeah, really
Nice
great to
meeting
meet
you.
you again.
Yeah, and also we have Ibu Trianisa here. Yeah, Ibu.
Yeah, good
Trianisa.
morning, everyone. Good
Hello,
morning,
yeah,
Ibu
good morning.
Tuzi.
Good
Yeah.
morning.
Megasari.
Yeah, good morning.
Right. Yeah, I think we and also all of our students, 7 of our students already here, and we also still open the class to anyone who wants to learn more about the research method in education with you, Associate Professor Dr. Mages Wari from Universitas Sains Malaysia. Okay, without further ado, I will give the time for Dr. Mages to discuss about quantitative data analysis, which will take very long discussion here. And yeah, hopefully we can cover all of the things today, but if it's not, we can still have some discussion later in the next meeting. All right, Dr. Mages, the time is yours now.
Thank you, Dr. Susi. Okay, right. Today I'm going to talk about quantitative data analysis. So welcome to the session. So last week we have started the previous 2 weeks. We have started with can hear me, right? Can you all hear me?
Yes,
Yeah, very
yes,
clear.
Yes, right.
Yeah.
It's clear.
Okay. So last 2 weeks ago, I talked about problem statement. Then from the problem statement, I bring it down to what you call that quantitative research, whereby I show the link between how to do a problem statement and at the same time how to write a problem statement according to the demands of quantitative research. So I think I did say that last 2 weeks. So you would got my idea is that from the last 2 weeks lecture, you would have got the idea of how to write problem statement for I'm not going to say the quantitative research in general, but quantitative research per se. There are many kind of quantitative research, so if you're going to use experimental design, the problem statement reflects the experimental design. If you're going to use survey design, from the problem statement, let's say I'm reading your work, okay, I'm reading your thesis or your journal article or anything. So from the problem statement, I will get the idea, oh, this research is a survey, or this research is a experimental design. So your writing must be as such. So I gave you a few examples, and also I taught how to go from research question to research objective and hypothesis, right? Now, continuing from there, we will see how we will connect a problem, question, hypothesis, and objective to the data analysis. So, end of this session, you must get the idea that there is a flow. It's not that problem standing by itself, the research design, standing by itself, and then your data analysis is something else, So if this is the case, you as a researcher, yourself as a researcher, you will know, oh, something is incorrect. Something is incorrect. As a researcher, if you can find the flow, the continuity from the research problem to the research design and to the data analysis, then you are on the safe side. So your research is a good research. It's just a matter of how you're going to justify that your research is good. You are doing the right thing. Okay, right. Now, so as I mentioned just now to Dr. Tuzi, when I talk about the quantitative data analysis, these are the topics that supposedly I must cover. So I can start from descriptive, inferential, hypothesis testing, errors, t-test, and all this. These are the things that I must cover. But I don't think I can cover everything. So these 3 parts maybe because these 3 it involves multivariate data analysis. So I thought of talking together with the factor analysis for next week. Okay, right. So let's look into descriptive statistic first. So descriptive statistic is the most fundamental statistic. Okay, most paling asas, most fundamental analysis right? So why we want to use descriptive statistic? So from the word descriptive, okay, from the word descriptive itself, the reason that you want to use descriptive is you want to describe a sample. If you remember last week, I talked about population, then I talked about target population, then I talked about sample, correct? So your sample must be random, usually for quantitative analysis, we use random sampling, okay? Probability sampling. So that means we are going to focus on certain group of people, right? Random means if you say secondary school student, you are randomly selecting secondary school students from the population of secondary school student. So if that's the case, when you say you are using descriptive statistic, you are describing the sample. So let's say you are talking about secondary school students attitude towards learning chemistry. Okay, so you administer the questionnaire, you collect the data, then you do the analysis. From the analysis, what is your finding of the analysis is you are getting the mean, or you are getting the frequency, or you are getting the central values of the sample. But you can't generalize to the population. The mean is just describing the sample. Okay, you must understand. That's why I'm stressing this part. There is a difference, You see, when you take the sample, your finding is very focused on the sample for descriptive statistic. You use mean, standard deviation, mode, median, and all that. So it's very focused on the sample. You can't actually generalize to the population, even though you take the sample from the population. Okay, right. Now, how are you going to describe the sample? So usually what we do, we use graph, we use charts, or we use there are three kind of statistic later I will show you. So basically what we are doing is you are taking let's say your sample, you have 100 students, so these 100 students, they have different attitude. So it is impossible to record 100 students attitude. So what you will do, you will administer the questionnaire, you get the finding, and then you record the summary. Okay, this summary describes the attitude of these 100 students. But using the descriptive statistic, using the descriptive values, you cannot generalize to the population. It is merely describing the sample. Okay, this is the most important thing. Or in other words, you can say, if you want to describe 100 students' attitude, one by one, it is so much. It's very difficult. So what you are doing is, we are taking the 100 data, we are reducing it to the mean, we are reducing it to the mode, or we are reducing it to the median. So that is the purpose of descriptive statistic. Inferential statistic, it is different. So inferential statistic, you are doing the analysis, you are testing the hypothesis, and you want to see whether the finding that you get from the sample can be generalized to the population. So this must be very clear. Later I'll go into the inferential statistic. Okay, so the difference between inferential and then descriptive statistic. So descriptive statistic is very focused on the sample that you are measuring. Using the finding of descriptive statistic, which is used frequency, mean, mode, median, it is quite impossible for you to generalize to the general population. It's only very specific to the sample that you are testing. So in other words, you are describing about the sample. So you are describing about the attitude of the students or sample, the 100 students. And then how are you going to describe? You're going to use mean, median, mean, mode, and so on. So it's very specific. That's why I say there's no uncertainty. So it's very, very, you can be very sure of your finding. Okay, right. Now, how are you going to describe the variable? How are you going to describe how to say attitude of the 100 students? So now I'm only talking about the sample 100 students. So there is two ways of describing. One is central tendency, another one dispersion. Dispersion is the spread. You know, that there is a normal curve, then you spread it. You know, it reflects on the spread. Central tendency is the central value, or another word we could say that if you have 100 data, you want to know where most of the data are. You know, that's called central tendency. Okay, kebanyakan data itu duduk di mana? That is called central tendency. Dispersion is the spread. How far it is from the mean value, you know. So the spread is wider, you know, you have wider spread. That means your sample got varieties of attitude. You cannot like say that majority of the students have a good attitude or majority of the students have a poor attitude. You have a very spread, you know, that the sample got varieties of attitude. It starts from low to high, medium, and so on. But if your dispersion is low, you know, closer to the mean, then you can say that, oh, majority of your students having average attitude, or whatever the mean shows. Let's say the sample you investigated got mostly the students have good attitude. So your dispersion will be lesser, you know. So the dispersion means spread will be lesser. So now I will talk about mean, median, and go specific on the dispersion. Okay. Right. Now, what is mean? So everyone know what is mean, right? Mean is average. You take the total sum and then you divide by the total numbers. So for example, you have let's say the income of people are something like this, 10,000, 10,000, 45, 60. Then the mean will be, you plus all the numbers and then you divide by the frequency. That means frequency is 1, 2, 3, 4, 5. Divide by 5. So your average income, I took it from the website. That's why it's United States. So it will be 225. Okay. So average, yeah, average. Right. So what is median? Median is the middle value. Okay. Median is the middle value. So in order to find the median, you need to arrange. You need to arrange the data from the smallest number, smallest value to the highest value. So from there, you can find which is the middle number. So in this case, you have to arrange 10,000 first, second 10,000, third 45,000, 60,000, and 100,000, right? So if you arrange them properly, you will find that 45,000 is the middle value. So the middle value is the mean. Okay, middle value is the mean. Modes, sometimes called modal. Modes is the highest frequency. The highest frequency. That means if you see this number, you can see 10,000 happens 2 times. Correct? But the others 45, 60, and 100, it just appears 1 time. So the highest frequency here is 10,000. So this is the mode. Okay, this is the mode. So I hope you can get the basic idea about central tendency. Let me repeat again. Mean is very simple. You just sum everything. Okay, sum and divide by the frequency. So 1, 2, 3, 4, 5. It's 5. Median is you arrange the numbers from the lowest to the highest. So you have the data, you arrange from the lowest to the highest, and then you will get the middle number. Okay. Now, in this case, you have 1, 2, 3, 4, 5. So you have 5 values. So it's not a problem. You get a middle number. Let's say you have one more. You have another one. Let's say it's a 200,000, right? So it will become 1, 2, 3, 4, 5, 6. 6 items. Okay, 6 values. So in this case, how are you going to find the median number? Median, the mid value. So it is an even number. So what will happen is, let's say you arrange this back, put this here, right? So you have 10, 10, 45, 60, 200, okay, and 100,000. So now the middle number will be 45 and 60. Am I right? The middle number will be 45 and 60. So what you need to do, you plus these two numbers and divide by 2. Then you will get the median, which is the center value. Okay. Then the mode is still 10,000 appears 2 times. So the mode is still 10,000. So mean is the central value. Mean is the average that describes the sample. Median is the central value. Mode is the highest number of frequency. Okay, right. So this is central tendency. So from the word central tendency, you need to know, you must understand, it is actually talking about what could be the average, or what could be the central value that describe the sample. Okay. Now dispersion is contradict or alternative, or it is the total contradict of the central tendency. If central tendency is totally focused on the central values, dispersion here talks about the what you call that, the distribution of the sample. So it is not focused on the mean or median or mode, but how far it is from the mean, or how far it is from the median, or how far it is from the mode. Okay. Now, how are we going to describe the dispersion? So dispersion we can describe using range, variance, standard deviation, and skew. Okay. Now we will look into all these things, but I will show the graph how it appears. But before that, you must know what is variant. All these things. Okay. Now, what is range? Let me go one by one. So, for example, central tendency. Central tendency, you see here in this graph, okay, in this graph, line graph, you can see that the second bar is the longest bar. Okay, so longest bar, it represents what you call that, the mode, median, and mean, right? Mode, median, and mean. So in other words, you can see that if you look at this bar, most of the data will be centralized in the second bar. Okay, so that means it has an implication on the sample. It shows that most of the samples falls under this category. Okay, right. Now, so I'm still in the central value. So I will go central value and what you call that, dispersion. I will talk about them interchangeably, because if I just focus on central value, you wouldn't able to understand dispersion. So I will talk about interchangeably. So I hope you will follow me. Right. Okay. Now, look at
Dr. Mages.
Yeah.
Dr. Mages, sorry to interrupt. Would you please set the slide, your slideshow mode? Thank you.
Sorry. I keep forgetting that. Right. Now if you look here, right. this bar, it is a symmetrical distribution. It reflects the symmetrical distribution. In other words, you can see that the mean is about 7. Okay, if you take 10 bars, the mean falls here. Okay, the mean falls here. And then you also will see that the highest bar is also at 7. So that means the mean, mode, median falls around this bar. So we can see the range of maybe from 6.5 to 7.5. Okay, so the distribution is symmetrical. Now, but if you see here, the mean is still 7. Okay, the mean falls around this range, but you will realize that many of the samples, they fall before 7. That means majority of the samples are between 4 to 7. So that means it shows that the sample skewed negatively, skewed to the left. That means the spread is wider to the left. So when the spread is wider to the left, let's say we talk about attitude. It shows that majority of the students having less attitude, or their attitudes is very far from the average attitude. Let's say the average attitude is 4.5. Okay, in the scale of a 5 Likert scale, the average attitude is 4.5. So majority are skewed to the left. That means majority are falling in between 1 to 4.5. So if 1 to 4.5, that means it shows that their attitude is at the lower end. Okay, now if you look here, let's say the mean is 7, median, somewhere around this area. If you see, it is skewed positively, it is skewed this way. So majority of the people are between 7 to 10. Let's say, so okay, the mean is 7. So the majority of the people are positively, their attitude reflect what you call that, they're having a positive attitude, because the majority or many of them are falling above the average value. Okay, I hope you understand. If you have any question, you can stop me here, because it's quite difficult to understand. So I'm showing 3 graphs here. The first graph is symmetrical distribution. Just now I talked about mode, median, and mean, right? So when it is symmetrically distributed, you have a very good normal curve. Okay, symmetrically distributed. It shows that the samples are let's say you have 100 students in your sample, almost all of them are falling, almost all of them are having closer to the mean. That means everybody's value are almost at the mean. That means if your mean, let's say you get about 3.5, 100 people falls around the 3.5. 75% falls around the 3.5. But let's say you are having skewed. Let's say your mean is something like 7. Majority of the students are having less than 7. That means your student's attitude is poor. In this case, it's skewed to the right. That means let's say your average value is 7. Majority of them are having more than 7. That means they are having a very positive attitude, more than 7. So that's what I'm saying. How you can describe using mean, mode, median, and how you're going to present the mean, mode, median. You can use a bar graph. Okay, you can use bar graph. Okay, right. Now, let's go to the range. So just now, hold on. Just now, when I talk about ways what are the measures for descriptive statistic? I mentioned the central tendency is mean, median, and mode. Then dispersion is range, variance, standard deviation, and skew. And dispersion is actually talking about the spread of the variable. We don't have mean, mode, we cannot talk about what is the average value, what is the highest value, what is the most numbers value. We are not going to talk about that, but we are going to talk about the range, where they're going to fall, how far they spread. So I did mention, hold on please. Okay, right. Oh. Hold on. Okay, so I will go deeper on the range, standard deviation, and variance. So range is actually, you're talking about the difference between the highest and the lowest. Okay, when you say range is the difference between minimum and maximum value. So you take the maximum value, you minus the minimum value, you will get the range. Okay. So if you see here, when the data is widely distributed, if you see the blue line, when the data is widely distributed, the range will be very far. You will get a huge range. You see the point on the blue line, and then you compare with the red line and green line. So if it's a blue line, your range is very big. You see the data getting the distribution or the spread is lesser, the range will be lesser. So you see the green line, the spread is very, very less. So you can see that the range also lesser. So the range for the green line is between 150 to 250. That is about 100. So if you look at the green line, it is about maybe 125 to 275. So it's wider. Okay. The blue is the widest. Okay. So that's called range. Now, standard deviation. So what is standard deviation? Standard deviation is actually described about how far the values lies from the mean. Okay. Standard deviation is actually, I'm not going to show the calculation. All these calculation, mean, mode, median, everything you can get it from SPSS. So that's why I'm not going to talk about how to calculate. You put your data in the SPSS, you will be getting the values. So I'm not going to go to it, but I'm going to explain to you how these things are usable in your research. Okay, right. Now, when you talk about standard deviation, you always present your data using standard deviation. So what is the meaning of standard deviation? Standard deviation shows that how far your data lies from the mean. So if your mean is like, let's say 200, so your mean is 200. So if you see for the blue, red, and green, all these three samples, the average is 200. Let's say it's about 200. Okay, but you will realize that the data, for the green one, the distance between the data, the spread, distance between 150 and 200 definitely lesser. So that means for the green one, the standard deviation is lesser. For the red line, if you see, from 200 to the end point, you can see it is further than the green line. And for blue, the standard deviation is even further. So let's say it's a midpoint is 200, and you can say how far it is deviating from the 200. So that shows that for the green line, the standard deviation is lesser. For the red is slightly more than green, but for the blue, the standard deviation is the most highest. So that means for the blue, the spread is very far. Probably you would not be able to describe your sample well because it is spread the frequency is like totally spread. So you don't know which is the highest mode or highest frequency. You don't know what is the median, and it's quite difficult to determine. Okay. Now variance. Now variance and standard deviation, they are almost the same. The difference is for the, if you see here, standard deviation is how far each score lies, so how far from the mean, right? But for the variance, it's about the degree of spread. So the key word is for the standard deviation, how far. It's only how far. But then for the variance, it describes about the degree. We have, if we say the variance is higher, that means the degree of differences is higher. Okay, right. So how can you find what are the difference between standard deviation and variance? Variance is the square of the standard deviation. Standard deviation is the square root of variance. Okay, right. So you no need to worry about how to calculate a variance, how to calculate standard deviation, how to determine the range and all that. It's not our problem, because when you run in the SPSS data analysis, all this value you will get. Our problem is how to use this value in our research. Okay, how are we going to use the values in our research? So as I said just now, the mode, mean, median is the central central tendency. It describes about the where the sample is positioned. Dispersion is range, standard deviation, and variance. It talks about the spread. Okay, so keep this in your mind. This is very important for you to use in your data analysis. Later, I will show you how we're going to use this. Okay, right. So this is another example that we can see that. So this is the test scores. You will see the mean is, will be this graph also almost normally distributed. Okay, almost normally distributed. We can say it is normally distributed. So you have even frequency before and after the mean. So the mean falls around here. You can see the central point, and then the mode will be the highest. This one, so how many numbers, and then the median. So median is the central point. So this is something like a simple example that you might want to go through. Okay, right. Now dispersion. Again, I want to talk about the dispersion. Right. So this is your central point, right? So from the central point, I'm showing two distribution here. So I'm hoping that you will get the idea of how the spread differs. Okay, how the spread differs between the two lines. Okay, two lines. So you will see the one that the shorter what you call that, the shorter peak is distributed far, and then the higher peak is distributed less distributed. Okay, so that's what I want to show you. Right. Now again, so I would like to stress this part, the negatively skewed, normal, and positively skewed. Okay, so if you see here, normal distribution, you will get this mean, median, mode in the central line. So this is the normal distribution. So you will see that the number of samples that falls before mean, and then the number of samples falls after mean, they are almost the same. So there's no skewing. So what you can say that based on the mean, median, and mode, you can actually describe the sample. Okay, this is a very good distribution where you can go ahead with inferential statistic. But in this case, you see that the mode, median, and mean. So you will realize that there are a lot of data falling far from the mean. Okay, they are falling far from the mean. So it shows that this data is not normally distributed. When the data is not normally distributed, then there will be a question. Can we conduct inferential statistic? Can this data used to perform Anova, Ankova, or whatever you want to do it later? So the first step of us checking the normality of the data is to ensure that the samples are distributed along the mean, median, and mode. Same thing, if the data is positively skewed, you will see that the data, many of the samples are not close to the mean, but they are far from the mean. So this creates the question of whether we can go ahead with the inferential statistic. So if your data is not normally distributed, you might not be able to conduct inferential statistics. So you need to do what? You need to collect your data. You need to recollect the data and redo the analysis. Or what you need to do is you can actually drop some of the outliers, the extreme values, you can drop them and then try to get a normal distribution. So when you manage to obtain a normal distribution, then only you can continue with the inferential analysis. Okay, so the three things of standard, three measures of central tendency is mode, median, mean, and then dispersion is range, standard deviation, and variance. You must understand all these 6 measures very clearly, so that when I go into inferential statistic, I will use the word variance, homogeneity of variance very frequently. So you would be able to link with what I'm my intention. Okay. Before I go to inferential statistic, any question on the descriptive statistic I can answer first, if you have. Okay, so I hope you get that clear picture. So again, I want to stress that you have your sample, you get the mean. That means it shows that what is the average. Let's say you are measuring attitude. Your Likert scale is 1 to 5. You get about 4.5. Let's say the average. So it shows that majority of your students are having a very good attitude. That's the mean. And then if what you call that, out of 100 students, 60 of them getting 4, let's say 4, that means 4 is the mode. Out of 100 students, majority of them, or when you arrange them from the lowest value to highest value, let's say they're getting about 4.3, so 4.3 is the median. Okay, so this is the central tendency. So how far it is away from the mean? Okay, berapa jarak dia daripada mean? If it's closer to the mean, we are getting normal distribution. But if it's very far from the mean, we can get negatively skewed or positively skewed. Okay, so the negatively skewed and positively skewed, it's quite impossible for us to get a normal distribution, right? So we must try to get as best as possible. So how to determine whether it is okay or not? There is a test to be done. But actually your standard deviation and your variance explains about the spread of the what do you call that? The spread of the data. Okay, right. So let's go to the inferential statistic. Now, inferential statistic is different from the descriptive statistic. If you look at descriptive statistic, it is just describing the sample. It's not population. You take the sample from the population, it describes the sample. So you got nothing to do with the population, right? But then what is the point of doing a study just describing a sample? Now what you need to do is whether the descriptive statistic that you get from the sample can be inferred on a population or not. You want to know that. So in order to do that, what you need to do is you need to conduct inferential statistic. So in any research, the first step is to conduct descriptive statistic. The next step is to look into the inferential statistic. So descriptive statistic, you have a sample from the population, you use appropriate strategy to decide your sample. Then from the sample, you already get your finding about descriptive statistic. You already know the mode, you already know the mean, you already know the range, the standard deviation, and so on, the variance. Now you want to know whether all these measures of descriptive statistic can be applied, can be inferred on the population or not. So what you need to do is you need to conduct inferential statistics. Okay, right. So if you want to do your research will be good. That's why I said the sampling strategies are very important. If your sampling strategy is incorrect, that will also create an issue of how can you apply or how can you infer your descriptive to the population using inferential statistics. Okay, then that will be a question. That's why always remember you need to use a right, appropriate, a correct sampling strategy. Okay, so let's go into the inferential statistic, right? So the basic fundamental is in any research we will start with descriptive statistic, but we won't stop there. We will continue the next step, which is inferential statistic. Okay, right. Now, so the accuracy, as I said just now, when you want to infer the finding from the sample, you want to infer to the population. The first criteria is the sample must be representative of the population. So let's say you have middle school students, 100,000. So if you want to generalize to the middle school students, you must ensure that the samples are representative. That means your samples, you are from the middle school students, they are from the various contexts. So random selection is very important. Okay, so you have your descriptive statistic. Now you want to infer to the population, you need to do the inferential statistic. If you want to infer, if you want to generalize, the sampling strategy is very important. Let's say you are incorrectly, let's say you want to use a purposive sampling. Now, if you use a purposive sampling, you have to think, how can you generalize the finding of the purposive sampling to the general population? But if you use a random selection or random sampling, you can easily generalize the finding to the population. So the sampling strategy and the samples that you going to participate in your research is very, very important. To ensure the descriptive statistic is inferred to the general population using inferential statistic. Okay, right. Now, two things in the inferential statistic that you need to know. One is, the first is hypothesis testing. So if you look at the descriptive statistic, I didn't mention anything on hypothesis. I just said that you're going to use mean, mode, median, and you're going to describe the dispersion. So how are you going to describe the dispersion? you're going to use the standard deviation, you're going to use variance, or you're going to use range. Only that I mentioned. But in the inferential statistic, the first difference is that inferential statistics involves hypothesis testing. Okay, hypothesis testing. So that means you have a hypothesis that is a significant difference pre and post test. Now you need to test. Okay, you need to test that. So in order to test, you have certain data analysis. Okay, that is the first point, hypothesis testing. The second point, you need to determine the significant level. Okay, so at what significant level are you going to reject, or are you going to accept the hypothesis? First, you decide on the hypothesis. Second, you decide on the significant levels. So the significance levels also implies on the probability, probability P equal to 0.05, or P is less than 0.05. P is more than 0.05. So based on this significant level, you decide whether to accept or reject the hypothesis. So again, going back to the normal distribution. So if your range is widely distributed, your sample is widely distributed, and then you have a normal majority of them falls into the midpoint, 75% quartile, midpoint, like the graph that I've shown, and you only have few on the left and few on the right, so that is the rejection region. So that is the rejection region. So the midpoint here, the central point here, the one falls, majority falls around the center here, that is the acceptance region. Okay, so two criteria that you need to two measures that differentiates between descriptive and inferential is, I didn't talk about hypothesis in the descriptive statistic. So in the inferential statistic, the first thing is you need to indicate the hypothesis. So how are you going to indicate the hypothesis? Like I mentioned last week, based on the literature review, whether you're going to reject or you're going to accept, there is a null hypothesis or alternative hypothesis. The second thing, once you have your hypothesis, you need to decide the significant levels. Is it 0.5? Is it 0.001? Or it is 0.01. So 0.05 means 5 in 100. Okay, 95%. Okay, if it's a 0.001, 1 in 1000 or 10 in 100 or something like that. Okay, this is the criteria that differentiates between descriptive and inferential statistic. Okay, right. So before going further, so the next step in the inferential statistic is I will go into Anova, I will go into t-test and all that. Okay, right. Before going to that, so I want to just make a conclusion differentiating between descriptive and inferential statistic. So descriptive statistic concern about describing a target sample or population. Inferential statistic making inference. So how are you going to make inference? Based on the what you call that, the analysis that I'm going to show later, which is Anova, Manova, and all that thing, right? Okay, so descriptive statistic, if you see the first slide that I showed you, it is very specific. You cannot say it is wrong. But inferential statistic, there are probability. That's why we have hypothesis. We can reject or we can accept the hypothesis. That there is a probability. You might be wrong. You can go wrong with your inferential statistic. Then we have type 1 error, type 2 error later. Okay, right. Descriptive statistics is just organized. You present the data in meaningful way. You have your mean and then you present your data. But for the inferential statistic, you are going to compare. You're going to differentiate the mean. You have two means. You compare the means, whether the means are okay or not. But in the descriptive, you just have one mean. You describe. Okay. So in the descriptive statistic, you don't have a probability value. You don't have a hypothesis to reject or accept. But in the inferential statistic, you have a hypothesis to probability score, either to accept or reject. Okay, right. So the measures are different. So the tools, the measures are different for descriptive statistic. The tools or measures are different for inferential statistics. So inferential statistic, I'll go deeper. I haven't tell you yet. I'm going to talk about the tools. Okay, so I'm going to start from the basic, which is t-test. Right. So this is the general picture about descriptive and inferential. I hope you can follow up to this point before I can go further on t-test and all that. Okay, right. Now, when we talk about hypothesis testing, okay, what are we going to do? So now I'm going deeper on inferential statistics. So I have done with a different descriptive. I'm going into inferential statistics, right? So as I said, inferential statistic, it has two features. One is making hypothesis and testing hypothesis. So when you want to test your hypothesis, you need to have what you call that. You need to set probability range. Okay, you need to set a range. Okay, right. So how are we going to test the hypothesis? That the way we're going to test the hypothesis is called inferential statistic. How shall I say? So the way you already set your hypothesis. Now you're going to test your hypothesis. So in order for you to do the testing of hypothesis, you're going to collect data and you're going to analyze the data. So the analysis, the kind of analysis that you're going to conduct is called inferential statistic. So the kind of analysis, that means after you collect the data, then you're going to do the analysis. The analysis that you're going to conduct, it can be ANOVA, it can be t-test, and so on. So that's called inferential statistic. So testing hypothesis is the first features of inferential statistic. Okay, right. Now there are two types of hypotheses. Null hypothesis and alternative hypothesis. So null hypothesis, you are saying there is no difference between your measures. If you have two means, okay, so whenever you are testing hypothesis, you always will have more than one mean. In the descriptive analysis, you have one mean. You only describe the mean. But in the inferential statistic, you're going to have two means. That's why you're going to have your hypothesis. So when you compare the two means, when you're saying there's no difference, that's called null hypothesis. But when you say there is a difference in the means, then you say that as a alternative hypothesis. Now, all these things are very important for inferential statistic. Okay. Now, so in order for you to accept or you're going to reject the hypothesis, it is based on the significance level. So the significance level, as I said, it can be 5% or it can be 10%. Most of the time we use 5%. You know, whether you're going to use 5% or whatever value you're going to use, you base on the literature. You fall back on the literature. What will be the best value for your study? Okay. Now, let's say we are facing on the 5%. Okay, we are falling on the 5%. So that means I go back to the graph here. Right. So this graph, so we are saying that anything that falls in the 95% we accept. Okay, anything that falls in the 95% we accept. Anything that falls in that 5 extreme percent we reject. Okay, anything that falls in the beyond the 95%, extreme 5% we reject. Okay, right. So if that's the case, we can see here that do not reject the null hypothesis if it falls within the region of 95%. So if it falls within the region of 95%, we accept. But if it falls beyond the region of 95%, that means that 5% we reject. So that's why we have alpha less than 0.05, alpha or p less than 0.05, and p more than 0.05. Okay, so that is the significance level. So you must understand the significance level. What is the meaning of significance level? So the significance level indicates that anything falls in that 5%, if your significance is 0.05, we reject. Anything falls on the 95%, we accept. So that is the significance level, the meaning of significance level. So you need to understand that, right? Okay, now let's say there are two common errors that can happen. You know, in the real situation, when you get your data, okay, in your finding, the real situation, it shows that you need to reject the null hypothesis. The null hypothesis says that there is no significant difference between the pre and post test. Okay, there is no significance between pre and post test. So by right, you need to reject the null hypothesis. But accidentally, what you did, you go and accept the hypothesis. You know, so you went and accept the hypothesis. So when you do this kind of situation happens, you are creating error. You know, or the other way around, the alternative hypothesis says that there is significant difference between the pre and post. Okay, there is significant difference between pre and post. But accidentally, by right, you need to accept the hypothesis. But accidentally you went and reject the hypothesis. So that is an error. So this is called type 1 and type 2 errors. So when type 1 and type 2 errors occurs, the whole research will go wrong. Okay, the whole research will go wrong. Because why? You are not able, you are inferring. That means you have your data, you have your descriptive statistic, but when you want to infer to the population, you are inferring incorrectly. You are not showing the real data. You are not showing the real analysis, but the finding shows something totally contradict analysis. You know, so there are two errors here, type 1 error. Another one is type 2 error. Okay, the type 1 error is that when the sample appear to show a treatment effect, in fact, there's none. So that means you are seeing the differences between the pre and post. You know, you are seeing the differences between pre and post. So when you see the differences between pre and post, so you are saying that, okay, I'm going to reject the null hypothesis. There is no significant difference between pre and post. But then the difference between pre and post is not because of the treatment, but maybe it is because of some other factor. Maybe the factor should be like, maybe it is like they have the students, they have like a prior knowledge, history, they have a prior input about the treatment. Do you still remember the threat to the validity I talked about last week? Yeah. So if you are not controlling the threat to the validity, type 1 error can happen. So maybe the sample that you choose is not, they already have some kind of experience. So you incorrectly choose the sample of the group that you're doing the study. By right, you should choose some other sample where you can get the real effect of the treatment. So the pre and post test differences that you're getting from this study is not actually representing your finding, but it is like it is caused by other external factors. Maybe the history, or the students are already getting the information from media, and so on. So you reject the hypothesis, but what you did is wrong. So that is called type 1 error. So type 1 error can be controlled if you can control the threat to the internal validity. So now you refer back to the last week class. What is the threat to the internal validity? Okay, now what is type 2 error? Type 2 error is actually the samples does not appear to have been affected by the treatment. The treatment does an effect, but the sample are not affected by the treatment. The samples are not affected by the treatment, but then the result shows there is some kind of finding. So this is mostly happen because of the small sample size. Okay, when you do the treatment with larger sample, probably you would not see any effect of the treatment. Okay, so let's say you have 200 students, your control group are 150, or experimental group 150. You don't really see the difference, significant difference. But then when you do a study with 30 students, your control group, another 30 students in the experimental group, you can see the difference. Difference between the groups. So the question is whether the treatment is creating the difference or not. If the treatment is really effective, whether you do with a small size sample or you do with larger size sample, the result should be the same, correct? There should be the difference between pre and post. But now when you do a study with small group, you see the difference. But then when you do the study with larger group, it seems there's no significant effect. So this is called type 2 error. So most of the time, type 2 error appears because of the sample size. It's not sample type, like the type 1 error more to the sample that maybe they would affected, or they get the information from the prior study, or they get the information from the media and so on. But this type 2 mostly because of the sample size. That's why in the experimental design or in the quantitative study, the sample size is very important. The first thing is the sample must be representative of the population. If not, you will get the type 1 error. If your sample size is too small, the possibilities of you getting type 2 error is there. Okay, in order to avoid the type 2 error, we do a study, we use a wider sample. Okay, right. So this is a brief summary of the type 1 and type 2 error. Okay, right. So you accept null hypothesis, how shall I present this? Correct conclusion is when you reject the null hypothesis, when there is no significant difference between the pre and post test. And then the correct conclusion is when you accept the alternative hypothesis, when there is a significant difference between pre and post test. So the two situations, you reject the null hypothesis when there is a significant difference. You accept the alternative hypothesis when there is a significant difference. So So that is the correct conclusion. But if it happens the other way around, you are creating type 1 error, when by right you should reject the null hypothesis, but you go and accept it. When you need to accept the null alternative hypothesis, you went and reject it. You know, so this is type 1 and type 2 errors. So in order to do your research, in order to do the inferential statistic, you must make sure type 1 error and type 2 errors do not appear, do not take place. You know, so in order to do this, we will have several analyses. Okay, so besides analysis, the sampling strategy is very important. Okay, right. Let me go into the analysis now. Now, do you have any question before I can go into the analysis? So I will go one by one, t-test, one or two way, ANOVA and COA and so on. Do you have any question? So now let's reflect back. I've talked about descriptive research. I've talked about inferential research. So if you talk about, if in the descriptive, I mentioned about mean, median, and mode, and the spread is, we are talking about standard deviation, range, and variance. When come to inferential statistic, I talked about hypothesis testing and setting the significance level. Okay, these are the two key points. And I talked about the error, you know, so when you decide on the significance level, or when you are testing the hypothesis, there are possibilities of type 1 and type 2 errors to take place. So how to control, how to ensure that type 1 and type 2 errors do not take place is to control the internal threat or external threat to the study. So in doing the data analysis, we also must make sure that the type 1 and type 2 errors can be controlled. You know, for example, t-test is comparison of two means. ANOVA is comparison of more than two means, right? In some studies, you can see that people avoid doing ANOVA, but they repeat the t-test few times. You know, so t-test is comparison of two means. ANOVA is comparison more than two means, right? In some studies, you can see that rather than doing ANOVA, the researcher might have repeated the t-test few times. So if this thing happens, there are possibility for type 1 or type 2 error to take place. So when you repeat the analysis several times, there are possibilities for you to do incorrect judgment. There are possibilities for you to reject. You might have accept the hypothesis by when you supposedly reject the hypothesis. You know, because why? You're repeating the analysis many times. Rather than repeating the analysis many times, we try to reduce the error of analysis by just doing one analysis, which is ANOVA. Same thing with the others. So that's why I talk about the errors first before I can go to the t-test. Right. Now let's go to the t-test now.
Dr. Mages, excuse me, can I ask a question?
Yes, sure.
Yes, a couple of months ago, we tested an undergraduate thesis. The research is about the effect of distance learning on students' learning motivation of science subject in junior high school, in one junior high school in a city. So the population in that study is the total students in that school. The number of students was 255 students. And then she collected the data with two questionnaires. One questionnaire is on distance learning, and the other questionnaire is on learning motivation.
Mm-hmm.
So she has two sets of data, and then she conducted t-tests. T-tests of those two scores, and then the conclusion is there is a significant effect of distance learning on students' learning motivations in that school. So the conclusion is drawn for that school. Is this study correct according to you methodologically?
Okay, so I assume that you would have done a descriptive analysis, and the t-test is the inferential analysis. Okay.
Yes.
Whether the study is correct or incorrect, it's very difficult to say. It's very difficult to say. But there is a lot of room for questioning. I can question the validity of your study. There are many rooms. For example, you said you measured motivation using a questionnaire.
Yes.
Then you are talking about distance learning. So that means you are looking into the effect of distance learning on motivation. Correct?
Yes.
Now I can question you. Motivation, definitely there are many subscales.
Yes. Yes.
Right. So merely doing a t-test, how can you say there is a significant? So probably a type 1 error would have occurred there.
Okay.
Because you're just doing a t-test and then you're assuming collectively the motivation as one single variable. But I can argue that there are many kinds of motivation, many subscales of motivation. So how can you simply use merely a t-test and you can say you are rejecting the hypothesis, a null hypothesis? So type 1 error. That's what I meant by type 1 error.
Yes.
You know, in the reality, there is no significant difference. But then, just because you use a statistic which is it's less robust, less rigor, you assume there is a difference. Okay. Now you follow my lecture, then probably you will get a better understanding of what I'm trying to say. Then you might go back and do a more advanced or more rigor analysis.
Okay. Thank you.
Thank you for the
Thank
question.
you, Dr. Mages. Yes.
Right. Okay. Right. Hopefully
Dr.
all of
Mages.
you are following. Yes. I would
Dr.
like
Mages, there's also one question regarding the error type 1 and type 2. You in your presentation you mentioned that there is a probability or a chance for us to do the type 1 error or type 2 error in the hypothesis test. The question is, when we're doing the research, how can we realize that we did that, or what do we have to do to avoid in that error?
Right. Okay, Dr. Suzy, can I answer the question?
Yes.
Yeah.
Sure.
Right. Like, can I? Your name is Monica, is it? Yes, huh? Okay, I refer to your example. Okay, I refer to your example. So just now, Monica mentioned that she's looking into the effect of direct distance learning on motivation. Correct? So we use that example. So when she conduct a research, she wouldn't know whether there are possibilities for type 1 error or type 2 error. She's not aware of it. You know, but as a researcher, you need to control, you need to take measures, you need to make sure your research is as rigor as possible. So it starts from the sampling, the kind of analysis you're going to use, and the interpretation you're going to make. So in a case, very good example, a case we can make it as a good example. She said a population is 2,500. Am I right?
255, sorry, Dr. Mages. Just from one school. Yes.
55. That is your population. What is your sample?
129.
129. Right. So the population is 255 and the sample is 129. The sample size is very big. Correct? If you compare 255 and 129, the sample size is very big. So we can say the sampling would not be a problem here, because the sample is enough, sufficient enough in terms of size to represent the population.
Yes.
Let's say she switched. Now the population is not 255. The population is the entire Indonesia, let's say. but a sample size is only 129. Do you think the sample size in terms of size represents, I'm not talking about the characteristic or the features of the sample, I'm talking about the size. In terms of size, it represents the entire population of the Indonesia? Probably not, right? Probably not. No. So if you want to do a study, entire population of a secondary school Indonesia, means you have to have hundreds, thousands and all that, correct, in terms of size. So if your sample size is incorrect, it can create type 1 error or type 2 error. Let's say her sample is 129, population is 255, but then let's say she just specifically used 4 classes. Like example, 4 classes. Another 2 classes, the rest of the students she ignored. She just don't want to do a study. So you see, the sampling strategy here is not random. It's not random. So she maybe she just want to do, it's easy for me to do the study with these 4 classes. I want to avoid that 2 classes.
Exactly, that happened, yes.
So it's not random. So when your sampling is not random, so there are chances to get an incorrect finding. So when you get your incorrect finding, that means type 1 or type 2 error occurs. Another one is using the statistical analysis. T-test is merely comparing 2 means. So pre-test mean and post-test mean. A preliminary study, I should say, okay, to conduct a preliminary study using t-test. But you want to infer to a wider population, probably t-test would not be appropriate. You need to go for another deeper analysis where the differences in the subscale level is to be considered. So if all these measures are not taken into consideration, the errors can happen. Okay, errors can happen. It can be a type 1 error or it can be a type 2 error. Dr. Tuzi, did I answer your question? Do you get the meaning behind it?
Yeah. Mm-hmm.
Yeah. Okay. So I hope the person who asked the question understands. Yeah. So it is not that I can say, oh, if you do this, you can avoid type 1. If you do that, you can avoid type 2 error. It's not that. It is collective. So that's why when we do the data analysis, we have to consider how can we avoid the type 1 error or how we can avoid the type 2 error. So I'm happy to answer the question because I get the idea. People are listening. Okay, right. Now let's go to the basic test, which is t-test. Now the t-test is the most fundamental. So when you do a t-test analysis, the chances for type 1 is there, the possibility for type 2 is also there. The analysis is not rigor. Okay, that's why when you go for publication, probably 10 years or 15 years back, you can make do with t-tests. But now there are huge statistical advances there. Statistical analysis has advanced very far. So you just use t-test, people will start questioning the validity of your study. So when I say validity of the study, how did you control the type 1 error? How did you control the type 2 error? So you're using t-test, you're opening yourself for more rooms for questioning. And it's very, very difficult to get into the impact factor journals if your analysis is merely t-test. So that's why another technique is to maybe you use t-test, but you have some supportive qualitative finding. So your study is not totally on t-test, but you have some qualitative finding that you can say, okay, if you say there is a significant difference, okay, the qualitative finding supports That's a trick there lah. Okay, so we use qualitative to support. So later part we will talk into the mixed method how we're going to do it. But now let me go into the t-test. There are two types of t-test. One is independent sample t-test, another one is paired sample t-test. Okay, I just give you an overall picture. When you do an independent sample t-test, okay, that means the two groups are independent. So in the quasi-experimental design, which I talked about last week, we have two groups, control and experimental. Okay, so these two groups are independent. They are not connected. They are two different groups. So if they are independent, you have your post-test square, post-test cost, and you have your pre-test cost. When you compare the mean of post and you compare when you compare the mean of post-test experimental and you compare the mean of post-test control, two different groups, that is called independent sample t-test. So usually for quasi-experimental design, when we use quasi-experimental design, we will have four scores. Pre-test for experiment and control, post-test for experiment and control. If you want to measure the effect of the treatment, you don't go and compare pre-test of the experiment and pre-test of the control. But what you do is you compare the post of the experiment and the post of the control. Then you can measure the effect of the treatment. When you compare the pre of experiment and the pre of control, you are not getting any information. You are just telling that they are equal prior to the treatment. There is no difference among them prior to the treatment. The differences only happens after the treatment when you compare the post cost of the two groups. So since these two groups are independent, so that's why we call it independent sample t-test. Okay, now I would like to stress here two independent groups. That means the groups are totally independent. They are not connected in any way. So your treatment that you use, you must make sure that last week I talked about threat to the internal validity. I talked about dilution of the treatment, or there is no communication between the control group and experimental group students. If let's say there is a kind of communication, they interacted. My teacher used computer to teach. Your teacher is just using an online is just chalk and talk. Mine is better. So that actually going to create some kind of interaction. If the interaction happens, there are possibilities for type 1 error to occur. Because in reality, there is no significant difference. But then, because of the interaction, your finding shows there is a significant difference. It's not because of the treatment, but because of the interaction. You see, so when your two groups are independent, they're totally not in connection. Then you use your independent group t-test. Another one is paired sample t-test. Paired sample t-test usually used for one group. Okay, you don't have two groups. I talked about pre-test, post-test design, single group design last week. So you have a pre-test, you have a post-test, then you measure the differences, mean differences between the pre and post. Okay, you are not comparing between two groups. Your t-test compared two means. That one you have to be very clear. T-test compares two means. Now, what are the means you are comparing? If the means are from two different groups, you use independent sample. But if the means are from the same group, you use paired sample t-test. So Actually, to tell you the truth, independent sample t-test would be a better measure to measure the effect of treatment compared to PET sample, because PET sample you are basically comparing one group. How you can say the effect measure is effective? But if you have a control group, independent sample, you are standing a better, you are doing a better analysis to say the effectiveness of the treatment. Okay, right. So two things: independent sample, PET sample. So this is examples that you might want to read in further. Right. Now, in order to conduct a t-test, before you conduct your t-test, now the first stage is you already gotten your descriptive statistic. You already have your descriptive statistic. Now, after you get your descriptive statistic, you want to test whether there is a significant difference using t-test. Okay, so the assumptions that you meet, your data must meet the assumption. In your writing, you must show the assumptions of the t-test are met. The first thing is dependent variables are interval or ratio. They are continuous data. Continuous means Likert scale, percentage and all that, continuous data. They are not dichotomy. They are not like it's like gender, income group. They are not dichotomy data. They are continuous data. The samples are normally distributed. I showed you the normal curve, right? Right. The samples are normally distributed. The samples are randomly selected. You know, the homogeneity of variance. The group have equal variance. Okay, the groups have equal variance. I will go deeper on this. What is the meaning of homogeneity of variance? Okay, right. So if you can meet all these things, then only you can conduct a t-test. Okay, so I think all this not a problem. Interval data are normally distributed, randomly selected. It's not an issue. I'm going to talk about what is homogeneity of variance and how are you going to determine whether your samples have equal variance or not equal variance. Okay, like for t-test, we do leave-in test. For if you want to do a t-test, you check the homogeneity of variance using leave-in test. If for Anova, there is a different way of testing. Ancova, there is a different way of testing. Okay, right. Right. So let me talk about the homogeneity of variance first. Hold on. Okay, so I want to introduce the homogeneity of variance first. Okay, now homogeneity of variance is actually, let me see, hold on, something happened. Okay. Hold on. Yeah, so homogeneity of variance, actually you will check using leave-in test. So this is the leave-in test. So when you run a leave-in test, if homogeneity of assumption for homogeneity of variance is met, that means you must get your value of for significance more than 0.000. So it should be more. There should be no significant difference. Hold on. There should be no significant difference between the variances in the group. Okay, so your hypothesis is there is no significant difference between variances in the group. So when you get your significance, the differences are not significant, that means you are meeting the assumptions that homogeneity of variance exists, then you can conduct the one-way ANOVA. Okay, so always remember, for you to conduct a t-test, the first step is to check the homogeneity of variance. So in order to check the homogeneity of variance, you do a leave-in test. Okay, you conduct a leave-in test. So for the leave-in test, your significance value must be more than 0.000. Okay, so the value must be above 0.000. So when the value is above 0.000, that means you meet the assumption that homogeneity of variance are controlled. Okay, so the spreads of the variance, the spread of the data among the two groups that you are comparing, or the two means that you are comparing, is equal. Do you understand? So I hope you understand. So this is homogeneity of variance. So for each statistical analysis, you need to check the homogeneity of variance. So for ANOVA and t-test, we use leave-in test. Okay, leave-in test. So don't ask me how to do leave-in test. Leave-in test you can run using SPSS. So you will get the finding. You just have to click the option on homogeneity of variance, and you will get the finding. Okay, so the key point here is it should be more than 0.000. So when it is more than 0.000, that it shows that you are meeting the assumption on the homogeneity of variance. Okay, right. Now let me go back to the assumption. So make sure before you conduct your t-test, all the assumptions are met. Right. So once you meet the assumptions, you need to check whether your research question, your research hypothesis are all tally. Okay, so I just want to go through the research question hypothesis for the independent t-test. Is there any significant difference between the post-test misconception score? Okay, so the post-test misconception score of the experimental and control group. So you're using experimental and control group, right? The independent t-test, and the measure is post-test mean score. So there is no significant difference. The other one is there is significant difference. Okay, the comparison is post-test scores of two different groups. So this is the research question, this is the hypothesis, can be null or alternative, and the key point here is comparison of the post-test scores of two different groups. Now, for example, right now I want to, this is the real data. So I want to compare a pre-test and post-test mean score of Arabdit is a questionnaire on misconception on climate change between control and experimental group. So before I can compare the mean, what I did is I did need to do the descriptive finding first. So in the descriptive finding, you can see that I have a pre-test, control, experiment. The total number is 36, 35. The mean is 5.47, 5.11. Standard deviation 2.20, standard deviation 2.61. So mean standard deviation reflects the descriptive property of the pretest. Okay, so you can see from here, this is the real data, how far the control group student spread from the mean. How far the control groups to the experimental group student spread from the mean, 2.61. So the spread is not, it's not large, it's okay, it's quite small. So it is normally distributed. From here I can say that I can see the normality. There is a way to decide, but from here I can roughly guess the data is quite normally distributed. And then when I compare the pre-test of control and experiment, I get the P of 0.870. So 0.870, it shows that the differences between the control and experiment in the pre-test is not significant. You know, so they are actually similar. the scores, the pre-test scores are almost similar, but when compare the post-test, the first is I get the mean and I get the standard deviation. I also can see that they are not dispersed much, and the p-value is 0.000. That means there is a significant difference between control group and experimental group mean. That means the differences between the mean of control and the mean of experiment is huge. Pre-test, the difference are there. The differences are there, but they are small. So it's not so significant, but in the post-test, the differences are wide. So they are significant. So I can say that the differences, the significant differences is because of the treatment. I can make a judgment. The differences are significant because of the treatment. But later part, I can question, how do you know it is because of the treatment, not about something else? And I can say that I control my internal validity, the thread. The sampling strategy is random. The sample I use 38 only. How can you say it is good enough to make inference? All these things should be in your interpretation of data later. So another example is you can see the down one. I have a control experiment, the same thing, compare the mean, 8.70, then post-test greenhouse effect, or something like that, So this is the, it's just another application that I want to go deeper. Okay, right. So I hope you understand the independent sample t-test. Now, paired sample t-test. Is there any significant difference between pre-test and post-test misconception score? That means pre and post. The mean comparison is pre and post-test mean score. There is no significant difference. There is significant difference. This is the hypothesis. You can use it as a null, or you can use it as a alternative. The comparison is between pre and post-test scores of single group. Okay, single group. Right. So, so this is the t-test. I think I'm done with the t-test. Do you have any question on the t-test before I can go into Anova? When I go to Anova, you will reflect the t-test better again. Okay, right. So this is a simple comparison of the t-test. Like, let me go to the Anova. Okay, Anova, there is two types of Anova, one-way Anova and two-way Anova. The difference between one-way and two-way Anova is one-way Anova is only one independent variable. Two-way Anova is two independent variables. Later, I'll show you the differences. The differences between one-way Anova and t-test is you are comparing more than two means. It can be 3 means, it can be 4 means, it can be 5 means. But the key word is more than 2 means. When you use t-test, it's only 2 means. Okay. Now, is there any significant difference between mean attitude scores between 3 classes? So now you have 3 classes. You're not only comparing the overall attitude, but you're comparing the mean of class 1, class 2, class 3, 3 classes. So your hypothesis will be there is no significant difference between mean attitude scores between 3 classes. So you are comparing 3 classes, there is no difference. Or there is significant difference between mean attitude scores of the 3 classes. Okay. Now, so comparison of mean is mean class 1, mean class 2, mean class 3. Just now is, I hope you can see the difference with the t-test, Right. Now, the assumption, dependent variable, continuous, then independent variable consists 2 or more categorical or independent data. So dependent variable is your attitude score, right? Your attitude. So your attitude now is what? Likert scale, correct? Let's use the example attitude. So it's a Likert scale. Independent variable is your class, the class 1, class 2, class 3. So it is actually categorical. You know, class 1, class 2, class 3. Okay. Now, dependent, you need to check the assumption. So normality. So whether the data is normally distributed. So there are many ways to check the normal distribution. So one of the way is Shapiro-Wilkie, skewness cutoff, histogram, and normal QQ plot. So I have explained about the normal QQ plot very lengthy in the pre-test and the post-test. Another way to check is using the Shapiro-Wilkie test and skewness and kurtosis. Okay. After that, you need to check the homogeneity of variance. So how are you going to check the homogeneity of variance? As I said, for the t-test and ANOVA, you can use leave-in test. So this is the leave-in test. So leave-in test, as I said just now, it should be more than your significant value. So if your significant level is 0.05, it should be more than 0.05. If it's more than, if your significance level you set as 0 or 0.01, it should be more than 0.01. Okay, so you need to check leave-in test in order to make sure the variances. Always remember, now you are having 3 means: class 1, class 2, class 3. That means you are having a distribution for class 1, you are having a distribution for class 2, you are having a distribution for class 3. So you have to ensure that the variances, okay, the spread or the differences from the mean for the 3 curves are equal or almost equal. So that's why you are rejecting the hypothesis. You know, it should be more than that, right? So in case, let's say you are not getting it, you are getting less than 0.05. You know, you're getting less than 0.5. So you don't go and throw away the data. You can actually correct the violation. You can correct the violation using Welch ANOVA as an alternative post-test. So once we do our ANOVA, we want to do the post-hoc to see where the differences. I will show you later. But if you are not meeting the assumption, you can use Welch ANOVA and Games Howell test for Turkey post-hoc. I'll show you. Don't worry on this. Okay. So my key point that I want to show is you must check for the homogeneity of variance. So before conducting your one-way ANOVA, make sure your dependent variable continuous, your independent is categorical, you check the normality of distribution, and you check the homogeneity. These are the assumptions, right? Now, so we run one-way ANOVA. Let's say we are doing one-way ANOVA. So here is the descriptive statistic. So we have 3 groups here: beginner, intermediate, advanced. 3 group, and we want to see their mean. Okay, we can see mean attitude or mean something lah, you know. So we can see from the descriptive statistic, the mean is like 27.2, 23.6, 23. So we can see there are some differences in the mean. And then we also can get the standard deviation. From the standard deviation, we can see the spread is not much. It's almost at the, you know, it's not much of a spread. It's only 3 points, you know, so it's not much of spread. Okay, from the range also we can see 22, 33. So the range also, the differences is only 10. You know, 33 minus 22, it's about 11. So it's not much as well. So from here, roughly, I can guess this distribution should be normal. To confirm, I need to do the skewness test, you know, to confirm. But roughly, I can guess from here. Right. So once I get this descriptive statistic is just describing sample. I want to know whether I can infer to the population. So since this is 3 means, I'm not using t-test, but I'm using one-way ANOVA. So the one-way ANOVA I conduct between group and within group t-test. So from the finding, I am getting the significance is 0.021. So 0.021 is actually more than 0.005, correct? So if this is the case, do you think the differences are significant or the differences are not significant? Because it is more than 0.021, the differences are not significant. Correct? So you see here, the mean shows different. There are small difference. You know, the difference is very small between the three groups. So I want to know whether the differences are significant or not. So I run ANOVA. So when I run ANOVA, I'm getting 0.021. That shows the differences are not significant. So I accept the null hypothesis. I'm not rejecting the null hypothesis. I'm accepting the right hypothesis, saying that the differences between the three means are not significant. The differences between three means falls. You know the 95% curve, do you still remember? I showed you 95% and 5%. The differences falls at the 5% range. So because of that, I reject. The differences are not dropping in the 95%, the bigger range. It's dropping in the 5% at the end there. So for that reason, I'm rejecting. Okay? I hope you all can understand that. Right. Now, after I get this finding, I want to know where actually, okay, actually when I get this non-significant, I no need to go ahead and do the study because I know already that means are not significant. But I want to know what are the differences among the group. Here you have three groups, right? Beginner, intermediate, advanced. I want to know whether the differences among the group, is there any significant differences among the groups or not? So I do Turkey. This is called post hoc test. Okay, post hoc test. I can stop here. You know, I can stop at ANOVA and I say there is no significant difference between the group. But I want to go deeper. I want to see if among the group, in between the group, is there any differences or not? So I compare. Oh, beginner, intermediate, 0.046, not significant. Beginner, advanced, also not significant. Then I compare intermediate, beginner, intermediate, advanced. You know, so I can go deeper and say whether to find where is the significant differences. But since this is not significant, possibilities of no significance are there. You know, so this is called post hoc Turkey. Okay, so in the case just now, if your assumption is not met, you can use Welch ANOVA as the alternative for post hoc. So in this Welch ANOVA, instead of using instead of using Turkey, you can use Games-Howell test. If your assumption is homogeneity assumption is not met. If it's met, no worries. You just can go into post hoc Turkey. Right? So now I hope you get a very clear picture how you go from the descriptive to go to inferential, and then you go go into the group comparison. You know, actually, if you look at the group comparison here, you are comparing beginner and intermediate. Then you are seeing the significant, correct or not? Then you're comparing beginner and advanced. You're seeing this whether it's significant or not. This is actually t-test. Am I right? This is actually what you're doing here is already t-test. You know, but we don't want to stop at t-test. We want to go one step ahead. We don't want to do the analysis separately, but we want to combine all the means together to see the differences. That's why we are talking about analysis of variance ANOVA. So I hope you get the picture now. Okay, right. Now, so how are we going to report? You can see that there was a statistically significant difference between groups determined by one-way ANOVA. So this is your and then a Turkey postdoc test revealed the time to complete the problem was statistically significantly lower after taking the intermediate, advanced, and compared to the beginners. Okay, so there was no statistically significant between intermediate and advanced group. So we report this and also we report this. Okay, right. Okay. Okay, now we go to two-way ANOVA. Okay, we go to two-way ANOVA. Now, in the two-way ANOVA, the difference between one-way and two-way ANOVA, as I said just now, the two-way ANOVA is you have two independent variables. Okay, you have two independent variables and you have one dependent variable. So actually, since you understand ANOVA already, you can actually do this one as one ANOVA, one analysis, okay, and the connecting DV and IV2 as another ANOVA, correct? So you can actually do two steps of ANOVA. But when you do two steps of ANOVA, what will happen is you are creating possibilities of you creating errors are there. You know, statistical errors. So in the actual fact, probably there is no gender effect on political interest, or there is no level, there is no effect of level of education on political interest in actual fact. But then your research says that gender has an effect on political interest. Why? Because of the education level. But in your study, you did not consider education level. You know, I repeat again. Let's say you want to measure the effect of gender on political interest. Okay, so the finding that you got is gender do not exhibit or do not have any significant effect on political interest. Whether it's female or male or not, it doesn't matter. It doesn't have any effect on political interest. The thing is, probably the gender alone might not have a political interest. But if you, a female highly educated and a female with less education probably will have effect on the in the political interest. So if you measure gender alone, it gives you a false finding. But when you measure gender and level of education in combination, it gives you a true finding. Okay, so that's why two-way ANOVA is very important. Actually, we can make do this as one way, another one is political interest at level of another ANOVA, but it will give a false finding. So it creates type 1 error or it creates type 2 error because depends on what kind of hypothesis you are stating. Okay, I hope you understand now, right? So it is exactly same like one-way ANOVA. The only difference is now we are having two IVs. Okay, now let me go deeper. So how are you going to state the hypothesis? Okay, hypothesis. So the first hypothesis will be considering the first IV. There is no significant difference in group means at any level on the first independent variable. So there is no significant difference in the means at any level of gender. Okay. Then go to the second IV. There is no significant difference in the means at any level of education. Okay. Then there is no interaction effect. So there is no interaction effect of gender and level of education on political interest. So actually the first hypothesis reflects one-way ANOVA. The second hypothesis reflects one-way ANOVA. The third hypothesis reflects the two-way ANOVA. Okay, so we are doing all collectively. So we are doing all collectively so that we can control the errors. We can control as much as possible so that the errors do not occur. Okay, right. Now we see here. So this is the again what I can say is a descriptive statistic. Okay, this is a descriptive statistic. So in this descriptive statistic, you have for male, you got two levels, which is male and gender. You have two levels, which is male and female. Level of education, you have three: school, college, university. School, college, university. So you have male from school, what is their mean? You have male from college, what is the mean? You have male from university, what is the mean? Okay, and then you have the standard deviation. So I could roughly guess the data is normally distributed, but I'm not sure. In order to confirm the data is normally distributed, you need to do the normality test, which is the kurtosis and Kunis, or Shapiro, any test, right? Then after that, you need to check for the homogeneity of variance. What you can do is, again, the leaving test, right? So the dependent variable is political interest, which is continuous scale. Male and level of education is the dichotomy scale. Okay, you have grouping, right? So you have to make sure that, right? Now, once your descriptive statistic is done, you go into the what you call that, two-way ANOVA. So for two-way ANOVA, you can see for the gender. So for the gender, you are getting 0.448. That means you can reject the first hypothesis if you state there is a significant difference or there is no significant effect of gender. Now you need to accept the hypothesis there is no significant effect of gender on political interests. I hope you can follow me. The first is gender. Now you see the first hypothesis here. There is no significant difference in the means at any level of gender. So this is the first hypothesis. So here you look at the first hypothesis on the gender. So you are getting 0.448. So you can accept the hypothesis there is no significant difference of gender. Okay, now you go to the education level. The education level is that less than 0.001. So there is significant difference. So you go back to the second hypothesis, there is no significant difference in the means at any level of education. You can reject the hypothesis there is no significant difference. Okay, the third hypothesis is interaction effect of the gender and education level. So when you combine them together, when you combine both the IVs together, you are getting 0.02. So in combination, they affects the political interest. So that answers there is no interaction effect. So you reject this hypothesis. So you see so you see here, this is ANOVA, one-way ANOVA. This is the finding of one-way ANOVA. This is the finding of two-way ANOVA. So you can get the interaction effect. Collectively, you measure whether to reject or accept the hypothesis. So can you see the difference between one way and two ways? Okay, let's say we just talk about gender alone. Yeah, there is no significant difference. But when you combine gender and education, there is significant difference. So education alone, significant difference. So it shows that in your interpretation of finding later, you can tell that it's immaterial. I'm a man or woman. As long as my education, I have a education, it decides on the political interest. Okay, right. Okay, this is two-way ANOVA. I hope I'm clear now. So then after that, you might want to go to the post hoc. You want to see where is the difference. Okay, you want to see where is the difference. So you can see that definitely you cannot see for gender because it's only two levels. Male and female is only two levels. Unless you got three levels of gender, then you might want to find out where the differences are. But here, college of education, a level of education got three levels. So you want to find out whether the differences is between school and college, school and university. You know, so you do the post of Turkey. This is actually your t-test ready. Correct? So you can see, oh, the difference are significant. When I'm at school, my political interest is different. But when I reach college, my political interest change. There's difference. Significant. No? When I'm school, my political interest is something else. But when I go to university, my political interest totally changed. Significant. When I'm in college, college and school is college and school and college and school is same. It's just negative the other way around. But college and university, yeah, it is significant change as well. Okay, so you can see where is the differences happens. So in conclusion, when you run two-way ANOVA, you are doing your one-way ANOVA, you're combining with two-way ANOVA and as well as the t-test. So we are managed to control as much as possible from errors to take place. Okay, so I hope you able to understand what I'm saying. Now, analysis of covariance. So what is the difference between ANOVA and UNCOVA? Okay, so t-test is comparison of two means. ANOVA is comparison of more than two means. UNCOVA, a two-way UNCOVA is ANOVA is same like ANOVA, but the only difference is you have two IVs now. Okay. Analysis of covariance is another extension of ANOVA, whereby you are controlling the covariate. Okay. So covariate here is something that can affect your finding. You know, now you want to know the effect of your treatment, right? You want to know the effect of your treatment on your students, right? So when you want to measure the effect of the treatment, you must make sure that anything that can interfere with your findings, that anything that can change the findings, you must control. So the variables or the measures that can affect the findings are called as covariates. So in the quasi-experimental design, when you want to compare or want to measure the effect of the treatment, one of the prominent covariate is the pretest. If the pretest is already very high, the students already have a very good understanding, definitely it will be reflected in the post-test. Correct? So you must take measures to control the pretest. So the pretest is known here as covariate. Okay. Another example is, let's say you're looking into the attitude. You're measuring the attitude. So you want to measure the attitude of what is the effect of your treatment on the attitude. So the gender probably is a kind of covariate. So male or female might have effect on the attitude that you're going to measure. So you're going to control the covariance. So you need to do the analysis and you need to control so that the pretest or the gender do not affect the finding. So controlling, doing another level of ANOVA, okay, by controlling the covariate is known as analysis of covariance, ataupun we call it as ANCOVA. Okay, now I'll show you some examples. So why do you need to control the covariate? Okay, why we need to control the covariate? So the reason is covariate might correlate with the dependent variable. So the dependent variable is understanding. So if you don't control the pretest, it might affect the understanding. Or if you don't control the gender, it might affect the attitude scale. So the covariate must be controlled. How you know which is covariate? Fall back on the theory, fall back on the literature. Past steady state or gender is one of the effect that I must control in order to measure the effectiveness of attitude. Okay, right. So this is covariate. Now let me show you. Okay, now the differences in the writing the RQ and hypothesis. Is there any significant differences between the post-test scores? So now you are still measuring ANOVA, okay? You are still measuring ANOVA, but you are adding on with the phrase after controlling the pre-test scores. There is no significant difference between post-test scores after controlling the pre-test scores. You see, I'm adding on. If you compare to ANOVA or t-test, the phrase after controlling pretest, there is no, I would not have included this phrase. But when you go for ANCOVA, you will have this phrase after controlling the pretest scores, after controlling the gender, you know, or after controlling the location of schools or something like that. You know, so whenever you have the word controlling, I would know that, oh, you are doing ANCOVA. You are not doing ANOVA. Okay, right. So how do you control? Now, before going to that, the assumptions, variance are normally distributed, skewness, variance are equal between groups, homogeneity of variance, relationship between IV and covariate is linear. So all these things you can determine using SPSS. I'll go a little more example using this. Okay, let's say for example, hold on, let me see where I can. Okay. Now, so I have two groups here. So a control group with 50 students, experimental group with 50 students, and I have mean 7 here, minimum value 7, 15, maximum 11, 18. The mean is 8.94. The mean for experimental is 16.42. Standard deviation is like 1 point something and 0.9 something. So this part is the descriptive statistic. So before starting with ANCOVA or before starting with any inferential statistic, the first step is you need to write down the descriptive statistic. So this is the real-time data. So post-test scores of students' understanding of acid base, right? So from the mean and maximum, minimum and maximum value, I know the range. Okay, 15 to 18, I know the range. So control group students, the range is wider. Experimental group students, the range is only 3, short, very short. So the mean, I can see 18.94. The mean here is 16 because they are reaching closer to the 18. So I can see that majority of the students have acquired, better understanding because this is the understanding test. So they are reaching closer to the mean. Okay, right. So in order to check whether the homogeneity of variance are met, I checked the leaving test, which is 0.158. So it is above the significant, above the 0.05. So I met the assumption that homogeneity of variance is met. After that, I checked the relationship. Okay, the relationship. So group and pretest. So group and pretest, the interaction ataupun the correlation between group and pretest is also not significant, 0.137. So it shows that the pretest do not actually correlate with the group. Okay, actually ANCOVA would be best when the significant value for the interaction effect is significant. That means less than 0.05. The best the best possible reason for you to use ANCOVA will be when your significant value is less than 0.005. That means you saying that there is an interaction effect between group and pretest. So the pretest affects the groups. But in my case, where this is the real data, I'm showing 0.137. The group actually do not affect, or the pretest do not affect the group. So actually I can just make do with ANOVA. No need for me to do an ANCOVA because the pretest do not affect the group. But I just want to do ANCOVA because I want to show them that I'm doing a rigor statistic rather than just doing an ANCOVA. So ANCOVA will best possible if your interaction group and pretest is significant because the pretest affects the group. So you need to control the pretest. In my case, I'm getting not significant. It does not affect the group. That means what I'm trying to say is relationship between IV and covariate is linear. This is the assumption. But my data showing there is no relationship. There is no significant relationship between pretest and group. So I can actually ignore ANOVA. I can just stop ignore ANCOVA and I can stop with ANOVA. But I'm not doing that. I want to do one step ahead. Okay. So I still want to go ahead with ANCOVA because the rigorous of the statistical analysis. I hope you understand what I'm saying. So this is my ANCOVA. So from my ANCOVA, I can see that for the group, I'm getting 0.000. So there is a significant difference for the there is a significant group difference between experimental and control. There is a significant difference between the post-test scores of the experimental and control. So that's why I'm getting 0.000. And then eta square is 0.964. That means the effect size of my treatment is 96.4%. Okay, 96.4% of the differences among the post-test scores is caused by the treatment and not anything else. Because pre-test is already controlled, the covariate is already controlled, so the covariate would not cause the effect on the treatment. Okay, right. So this is ANCOVA. Right. So the next is repeated measure design. Oh, I don't think I can reach up to the next one. Let me cover the repeated measure design. I can continue with the next analysis the following week. So repeated measure design is exactly like ANOVA. ANOVA is the fundamental. Another level is ANCOVA, and another level is repeated measure design. So all this you are trying to do this kind of analysis so that you are trying to control the error type 1 and type 2 error. Okay, right. So is there any significant difference between pre-test, post-test, post-test 2 mean score? Okay, there is no significant difference between pre-test, post-test 1, post-test 2. So as I said last week, now you are comparing time series. Time 1 pre-test, time 2, post-test 1, time 2, time 3, post-test 2. Okay, but your treatment is still the same. Okay, the kind of treatment that you're using is still the same. The level, the student, the group of student still maintain the same. Okay, right. So you do the descriptive statistic again now. So your descriptive is like your mean value. This is real-time data. I just took one of my analysis. So I'm getting 66, 74. I can see the mean is increasing. At the pre-test, their mean is 66.31. Then post-test 1 slightly increase. Post-test 2, oh, their increase is higher. So you can say that consistent exposure to the treatment, they improve their understanding. I can make the assumption. Then after that, after you checking this distribution, then you need to check the assumption. The assumption is still go back normality. Normality, you can use the skewness and kurtosis. I'm not showing here. And then for the homogeneity of variance, for the t-test, Anova, Ankova, we use leave-in, correct? Leave-in test. But for repeated measure, we need to use moles. I don't know how to pronounce this, test of sphericity. Okay, this is the test that you need to use to check the distribution of variance for repeated measure design. Okay, so maybe this one I will go deeper on next week. So next week I'll go deeper on it. So for this, we must make sure whether it is significant or not significant. So if it is significant, we need to do the correction. If it is not significant, we can go ahead with our repeated measure analysis. So in this case, it shows 0.000. So the correction was done using greenhouse geyser. So greenhouse geyser was used to do the analysis, the correction, because here must be more than 0.00, right? To meet the assumption, the homogeneity of variance, it should be more than 0.00. So what I'm getting is the assumption is not met. It is violating. So I need to do the correction. I can choose either one of these and then I do the correction. Okay. After doing the correction, I run repeated measures. Okay, comparing. So what I'm getting is 0.000. That means there is a significant difference between the pre-test, post-test 1 and post-test 2. So my eta square is 0.77. 77.4% of the differences in the mean between pre, post 1 and post 2 is caused by the treatment. Okay, then I continue doing the post hoc. I want to find where is the differences are. So there is post-test 1 and pre-test is significant. Post-test 2 and pre-test also significant. Post-test 2 and post-test 1 also significant. So that means a treatment is a very good treatment. It actually creates significant difference across. Okay, so this is repeated measure design. So you need to have a holistic, I hope you can get a holistic picture now. Pre-test, t-test is just a simple comparison of two. When come to Anova, it is extension of t-test. Two-way Anova is extension of Anova. Ankova is another extension of Anova. And repeated measure design is the time series, which is another reflection of Anova. You can see the process are all similar. Only thing there is a twist and turn here to show the robustness of the analysis and to show that you are able to control from making errors, type 1 and type 2 error. Okay. Right, I think I'll stop here for today. I will talk a bit more on the repeated measure before I go to multivariate analysis next week.
Right, okay, thank you very much, Dr. Mages.
Thank you.
Okay. I think we have to take a deep breath. Yeah, Anova and Kova, and one-way repeated measure is the last presentation from Associate Professor Dr. Mageswari for today's lesson. Yeah, I think we still have 5 minutes. Is there any question from the audience or the students? Dr. Mages, hopefully you still have time, like 5 minutes.
Yeah, sure, no problem.
Yeah. Yeah, is there any questions from the students? Or from the other audience? Yes, you also made to, like, from the lecturers and other colleges from other university as well. Bu Monica, do you have some question?
Iya, izin bertanya ya Bu Tuzi. As Dr. Magas, actually in the beginning of the lecture today, I had one question that, is it true that we cannot submit to impact factor journal some descriptive studies anymore? Then you answered that an hour ago that, yeah, maybe 10 years ago, we can still submit descriptive studies to impact factor journal, but not now, not nowadays. They probably will reject the study. So if we are going to do descriptive studies, for example, we want to study alternative conceptions or motivations or interest in science lesson, then how would you suggest us to improve the depth of studies in order to get published in impact factor journals?
Okay. Okay, Monica, Miss Monica, I'm just sharing my experience now. I've been publishing for past 10 years, 10, 12 years since I complete my PhD. So I can see the shift in the trend, publication trend, you know. Those days, like the data that I showed earlier on the climate change and all that, I just used t-test and Ankova. It's a very basic, you know, and I published the finding is published in a Environmental Education Research Q1 journal, you know. I cannot do the same thing now. If I do the same thing now, even the editor will reject. The paper would not be sent out to review, you know. So because of the competitiveness, unless you are doing something very, very new, like for example, you are talking about something on COVID, let's say something on COVID, but then your COVID information is very focused on the community that you are investigating. So the community actually have some unique, they are exhibiting some unique features about COVID that you feel like that you want to tell or disseminate the idea. In that case, probably descriptive can make, I wouldn't say yeah, there are huge possibility for no, but since the finding is so unique, some part of the world, you know, any part of the world also would not be able to get that kind of finding. Only your particular sample that you are investigating, exhibiting that kind of, you might stand. But if it is just normal alternative conception, misconception, attitude, I don't think we can go for what you call that, descriptive. A normal, ordinary, mean, median, t-test and all that. What you can do is now they are going into this second level data analysis, whereby people are introducing SEM, structural equation modeling, PLSM. So this is second level, second generation statistical analysis. So in science education or in chemistry education, not many people have actually ventured into all these things, you know. So that would be a good survey when you want to do a survey or describe about the population. That will be a good approach. But also you have to understand, my experience, like recently I submitted 2 articles to Research in Science Education. So Research in Science Education is Q1 journal. Both the articles got rejected, you know, and in both the articles, I use PLS-SAM, you know, partially square structural equation modeling analysis. So I was thinking, oh, if I look at Rice, some studies people have used structural equation modeling, but many of them, I think there's no PLS partially square. Nobody have used that. So I was thinking, okay, if I do analysis using PLS, I stand a high chance to get published. But my assumption is wrong, because there's not many people in science education knows about PLS. My paper got rejected. Didn't even send for review. My first paper sent out for review. I know already. I got the idea. Oh, I think they are not well versed in PLS. My second paper didn't even send out for review. The editor itself rejected. Then what I did, I took the paper, I sent to another journal, Asia Pacific Education Researcher. This is Q2 journal. Now the papers are under review. I sent to this journal because I see many articles published on PLS. So I got this understanding. I assumed that, oh, since these people are many people in many articles in this journal using PLS, they might be able to understand what I'm doing. So for science education, it's very difficult to say, because if you see when you go for research in science education, all these top-notch people in science education, I'm not sure how well they have updated with statistical advance. You know, the advancement in statistical, the statistical advancements probably they wouldn't know, because these people are, maybe they have their own thinking, you know, science education must be like this. Oh, they must have a qualitative data, the quantity is like this, you know. So they cannot come out from that kind of thought, where people have ventured, you know, different dimension of research. You know, so to answer your question, if you want to just go on a descriptive, the best way to do a descriptive is using a qualitative in science education. You might have a quantity, a very few data, but you have to go in depth on a quali survey. You know how to do quali survey? You do an interview and do a survey, something like that.
Okay, thank you, Dr. Mages. Yes.
Right.
Okay. Terima kasih, Bu Tuzi.
Ya, sama-sama Bu Monica. Alright, Dr. Mages, actually I also have a question regarding the limitation of the number of the participants involved in each stages for all of the data analysis. Yeah, is there any limitation? But probably we can talk about this next week.
It's okay. I can just simply say.
Okay.
No,
Okay.
The thing is, like, I cannot tell you this is the number, you know, because the research method book, like from Crashwell or like from Gay and Harrison, all these people they mention, 30 in a group is good enough. But you see, again, we want to control ourselves from making type 1 and type 2 errors, right? Would it be appropriate just to do a study with 30 people in one group? So when you do a study with 30 people in one group, probably you might get the treatment is effective. But then you repeat the treatment with, let's say, 60 people in one group, you might get a totally contradicting finding. So type 1 error occurs. You know, so you need to have a sample size good enough in order to avoid from making this kind of errors. You know, like for PLSM or for structural equation modeling, the sample must be as big as, the larger the sample is better. But you can also do a study with 150. But using 150, would I be able to get an accurate finding? That's the question. You know, so it's very difficult to say this is the sample size. You know, like for example, if like this study, I think this study, I think I did with this is 90. If I remember, there's one study I did. This 50. The sample size is 50. You know, I had a lot of problem of getting this data published because the data is already published. I had a lot of problem to get this published because the reviewer keep telling me your sample is only 50. How can you say your sample is good enough? You know, so what I did, I had, if I remember very well, I had a qualitative finding to support. You know, to say that, okay, from the quanti finding, I'm getting the treatment is effective. But then you are telling that the sample size could be one of the reason, because I do with the smaller sample, I'm getting a good finding. So how can you ensure this one is, there's no error, there's no type 1 error occurring? Then what I did, I had some qualitative finding. I can't remember it's whether it's an open, it's an interview or open-ended test or something like that. I supported. I said, okay, in the open-ended test or the interview, this is the answers the student give. So the answers directly reflects on the treatment. So I said, so this is how we justify. You know, if not, it's very difficult to say what will be the best sample size. No.
Okay, yeah, thank you very much. So yeah, the minimum is 30.
Yeah.
But if you want to make our data more fruitful and have a better sound, yeah.
Yeah.
And yeah, we should increase our data number.
Yeah. So it falls back again. You know, just now you asked me the question: how to know, how to control, or what we should do to make sure we don't commit the type 1 and type 2 error. So these are the things. You know, so as long as you can control all these variables, as a researcher, you have the control, you have measures to control all these threats. You are controlling your type 1 and type 2 errors. Mm-hmm. So your research is valid.
Yeah. Right. Okay, students. There are lots of notes, yeah, that have to be considered in determining our research in the next future. So hopefully we didn't deal with the 1 or type 2, or maybe we know how to avoid type 1 and type 2 error in doing quantitative research. Yeah, we in this presentation, Dr. Mages also including some of her experience from some of her data, yeah, Dr. Mages, yeah, from kind of publication that she already made, so we can learn from the real example, yeah, Dr. Mages. Thank you very much for everything. Yeah, if you still have some question, please don't forget to write it down for next week meeting. We're going to continue the discussion about data analysis in quantitative, as well as the instrumentation, yeah, in quantitative research. All right, Dr. Mages, thank you very much for your time. Thank you very much for your regardless effort. Yeah,
hopefully you
so much from you, Dr. Mages.
Thank you. Hopefully you understand what I'm trying to say. I'm trying to say so much. I know it's very heavy, but I suggest you go through the PowerPoint. That's why I repeated many times, so that you can grasp the embedded meaning. Sometimes I can say, oh, descriptive statistics, but you wouldn't know what is actually I wanted to say. That's why I keep repeating many times, so that you understand what I'm saying. What is central tendency? You know, I can say central tendency is the center value. and I can go to next one. But what is the center value? How does it affect on my research? You wouldn't know. How from the descriptive you move to inferential? I can say from descriptive you go to inferential, but you wouldn't know the continuity there.
Yeah.
So that is very important. For me as a researcher, I feel like I need to get the overall picture of what is happening. Then I can go, okay, this is Anova, this is Anova, this is Manova, and so on. So that's what I'm trying to do with y'all also. Hopefully it reaches you.
Yeah, I hope so. Thanks to technology, if you still have some question or you want to go back to Dr. Mage's presentation for today, Dr. Mage's lecture, you can visit Departemen Pendidikan Kimia YouTube channel, but don't forget to like and subscribe. Okay. Yeah. All right. Okay, thank you very much, everyone. Thank you very much, Dr. Mages, Bu Hernani, Bu Monica, Iklima, Ibu Triana,
Terima kasih.
and everyone here. See you next week.
Yeah, thank you.
Method at the same time, okay?
Okay, bye-bye. Bye-bye.
Bye-bye.
Okay, terima kasih Ibu Hernani.
Terima kasih.
Terima kasih.
Thank you, Prof. Magas.
Bye-bye. Bye.